Welcome to this comprehensive masterclass on mathematical economics. Today, we delve into one of the most fundamental tools in an economist's toolkit, the power rule for derivatives. Mathematics is the language of economics, allowing us to quantify change, optimize behavior, and predict market trends with precision. To understand the power rule, we must first understand the concept of marginalism. In economics, we rarely ask, how much do I like food in total? Instead, we ask, how much more utility do I get from one more bite? This one more unit is the derivative. Whether it's marginal cost, marginal revenue, or marginal utility, we are looking at the slope of a function at a specific point. Let's define the rule formally. If we have a power function of the form f of x equals x to the n, where n is any real number, the derivative with respect to x is f prime of x equals n times x to the n minus 1. It's a simple yet powerful transformation. Bring the exponent down as a multiplier and subtract 1 from the original power. Why does this work? Mathematically, it emerges from the definition of the derivative using the difference quotient as the change in x approaches 0. For a square like x squared, the change is represented by the expansion of its area. As the increment becomes infinitely small, we are left with the perimeter's contribution to growth, which is 2x. Let's apply this to our first economic example, utility theory. Suppose a consumer's utility is represented by U of q equals q to the 0.5, representing diminishing returns. Using the power rule, the marginal utility is 0.5 times q to the negative 0.5. Notice how as quantity increases, the marginal utility decreases. This is the mathematical proof of why the first slice of pizza is better than the 10th. Now, consider production theory and costs. A typical short-run cost function might look like c of q equals q cubed. Applying the power rule, the marginal cost is mc equals 3q squared. This tells us that as production scales, the cost of producing the next unit increases at an accelerating rate due to factors like inefficiencies or limited factory space. The power rule also governs revenue and elasticity. If a firm faces a demand curve where price equals q to the negative 0.5, the total revenue, r equals p times q, becomes q to the 0.5. The marginal revenue, found via the power rule, is 0.5 times q to the negative 0.5. Understanding these slopes is crucial for firms to find the profit-maximizing point where marginal revenue equals marginal cost. What if the exponent is negative? In economics, inverse relationships are common. If y equals 1 over x, which is x to the negative 1, the derivative is negative 1 times x to the negative 2, or negative 1 over x squared. This is vital when studying how demand responds to price increases in highly competitive markets. Finally, we see the power rule in the famous Cobb-Douglas production function, y equals a times k to the alpha times l to the beta. When we take the partial derivative with respect to labor, we treat capital as a constant and apply the power rule to l to the beta, resulting in the marginal product of labor. This single rule allows us to calculate how much a new worker adds to the national GDP. In summary, the power rule d dx of x to the n equals n times x to the n minus 1 is the engine behind optimization in economics. From individual consumers to global conglomerates, calculating the rate of change is the key to making rational, data-driven decisions. Master the math, and you master the logic of the economy. References: 1. Alpha C. Chang and Kevin Wainwright, Fundamental Methods of Mathematical Economics. 2. Newt Sadister and Peter Hammond, Essential Mathematics for Economic Analysis. 3. Hal Varian, Intermediate Microeconomics, A Modern Approach. 4. Gujarati, D.N., Basic Econometrics.